Welcome to the viewers. Today we discuss an interesting nature of the Poisson bracket. The actually basic properties we derive. These properties are given below. Number one is property of linearity. So which we have to prove. Suppose in the bracket w plus w dash v, that will be bracket of wv plus bracket of w dash v. Then how to prove? Now from the basic definitions of the Poisson bracket, we write w plus w dash and v by the definition sum of I equals to, suppose if you are writing here I equals to 1 to up to n by the definition of Poisson bracket, del actually if you are taking in this way qy w plus w dash, that's a derivative, partial derivative with respect to del qy, del vi, del pi minus del of w plus w dash, that is del pi of w plus w dash, and del v del qy, that will be equals to, if we are breaking sum of I equals to 1 to up to n for the distributive property, del w del qy plus del w dash del qy and del v del pi minus del w del pi plus del w dash del pi del v del qy, and if we are breaking the bracket sum of I equals to 1 to up to n, what will happen there? Del w del qy del v del pi plus del w del qy del v del pi minus del w del pi del v del qy minus del w dash del pi del v del qy. Now arranging sum of I equals to 1 to up to n, del w del qy del v del pi. Now here del w del pi del v del qy, it is one term, and another term will be sum of I equals to 1 to up to n, del w dash del qy del v del pi minus del w dash del pi del v del qy. Now it is, we are in the shape of Poisson bracket. By definition, Poisson bracket of wv plus here Poisson bracket of w dash v. So we already proved Poisson bracket of w plus w dash v is equals to w plus v bracket of plus Poisson bracket of w dash plus v. So in this way we proved the property of linearity, and all detailed informations how this will come already derived in my earlier videos, so I don't discuss it further. Now for the another property, that's a property of linearity. There are the two things is there, you know already, in vector spaces. This is the first part of proving the linearity property. This is the first part, and another part is either we are writing the combinations or we writing in this way. It is a linearity property property of linearity. It is the first part, and another we have to prove for a scalar function. If we are writing in this way, CW and V is equal to CUV, WV, where C is a constant. So, for the second criteria to satisfy the linearity property, we have to prove it. And now we prove the first criteria of linearity property. Now let's prove for the second property. Now we are writing here Poisson bracket of CWV by the definitions, sum of I equals to 1 to up to n del Qy of CW and del V del Pi minus del Pi of CW del V del Qy. Now here it's clear, sum of I equals to 1 to up to n C del W del Qy del V del Pi minus C del W del Pi del V del Qy. So C of this del W del Qy del V del Pi minus del W del Pi del V del Qy. So it's clear, we are going in the shape of the Poisson bracket definitions, that is a bracket of VW. So finally we prove the second criteria to satisfy the linearity property. This is the second criteria. Now finally we declared that Poisson bracket is linear. Hence we can say Poisson bracket is linear. So today we end our classes. Thank you.